So first, let me thank Professor Kim for the invitation. So it was very nice to be here. I'm going. Should I put this lower, maybe, or how about here? Is it better? So I'm going to try to keep this lecture as elementary as possible. So in principle, you should be able to understand everything, and if not, you stop me and you ask questions. So the general topic is to try to understand systems of conservation laws. So you can think of U to be a vector valued function, T to be a time variable, X to be a special variable. And we are interested in getting solutions where this system of conservation law is satisfied, so say with 0 on the right-hand side. But what is well known is that if you try to solve a system of conservation laws of this form, where f is a nonlinear function satisfying some hyperbolicity conditions, so in such a way that waves propagate, nonlinear waves propagate in solutions of that system. So indeed, if you only look at that part, you will see shocks to appear. So there is no smooth solutions defined for all times. But even if you start with something smooth, you will have shocks, you will see shocks that form in finite time, and therefore you need to look for weak solutions of this PDE. Okay? Now, what I want to do here is to define these weak solutions, so to understand what are the admissible shock waves that should be used in a specific, say, physical theory. And to do that, I somehow make the PDE nicer. Okay, so I add more terms to the PDE, which is what is written in the right-hand side here. And more terms means that I'm adding not only one special derivative, but maybe 2 special derivatives, or 3, or even more. And more than that, this expression here could be nonlinear. It could also depend on U, actually. And it could be a nonlinear expression in terms of U, derivative, first order, second order, etc. Okay? And the question I'm asking is, what happens when the small parameter, epsilon is supposed to be small, when the small parameter epsilon goes to 0, what we expect is that this will be gone in a limit, so we will end up with a solution of the hyperbolic systems of conservation laws, only this part. So I'm going to call U this limit, and this limit will be discontinuous, and typically U epsilon will be smooth, U will be discontinuous. And by doing that, what you are doing is that you are actually choosing a selection criterion to decide which shocks that may satisfy the system of PDE, which of them are actually physically relevant, or say mathematically relevant in terms of a specific regularization on that side. Okay, so this sort of approach is of course very classical if you only ask for a second order approximation here. So if I'm only putting epsilon U xx, this is a second order parabolic regularization. And so it's, you know, smoothness of solutions is to be expected and can be proven in many cases. And this is exactly the way that the classical, so-called classical entropy conditions are introduced, and this go back to work in the 50s, in the 60s, 70s, 80s, etc., by all these people and maybe others. And the game here is precisely to do what I was telling here, to find conditions, algebraic conditions on the discontinuities of the weak solutions that will tell you, you know, which are physically admissible. Okay? So somehow I want to redo this sort of analysis, but not by adding only 2 derivatives, but by adding more terms. Okay? So this is a general problematic that we are asking. Now let me jump over, let's say, these 2 things and show immediately the basic examples. I go back to work by Marshall Slemrod, who is now a member of this department. And so the basic model you could keep in mind is the system of conservation of mass and momentum for a compressible fluid. And so this is this part, what this part is saying. Should I?
It seems that why we have a speaker over there just in front.
So should I move to a different place?
So how much
You want me to sit, to stand in another place? No?
This thing, I don't know. So if you...
Right, it's more difficult to see the screen, right?
Or in the middle. Or
maybe here, right? Would that be nice, better here?
The speaker makes that. I don't know why they put, So it's away from the speaker. That's the...
I see, so maybe that side would be fine, right?
Always the speaker. Yeah, it looks fine.
Looks fine, okay.
Sounds fine.
Can you still hear me?
Yeah.
Okay, so I was talking about an example, right? So this is a typical example that we have in mind. We have a fluid, a compressible fluid. It is described by two conservation laws for the deformation gradient W and the velocity V. To close this part of the system, you need to prescribe the stress as a function of the deformation gradient. And a typical requirement is that this stress will actually be a non-monotone function of W. Okay, so given this part, what I'm doing here, or actually what Marshall Slemrod was doing, he advocated the use of this regularization. So instead of what people were doing before, to add, say, epsilon Wx x and epsilon Vxx, he suggested that we should put 0 because this is like conservation of mass. There should be no diffusion on the mass equation. And on the second equation, what we are adding here is a coefficient of terms that takes into account the capillarity forces in a fluid. So that gives us a nice regularization that is exactly of the type I told you about before. And then the questions were the same as what I've been telling you in the first slide. Make an analysis of that system when this parameter alpha is fixed and epsilon goes to 0, and you want to understand what sort of weak solutions are picked up in this singular limit. And this work was done by Slemrod, Shearer, Treskinovsky, Abeyarat-Nenows, myself, with various assumptions. So this is what I'm talking about today. This is a typical example that we can have in mind. So let me now return to tell you that now a rather extended theory has been developed for these problems. And so let me first say that in general, so we are talking again about that system, and have a general system where U is vector valued, and I'm adding not only the second order term, but I'm also adding a third order term of this form, okay? Or could be even higher order. So what happens if you do that, if you have two effects that enter in a competition, two derivatives, this diffusion term, will actually introduce some smoothing of the discontinuity. So this is what this term here is doing. By adding another term with three derivatives, we are now introducing oscillations. Okay? And what you see is a competition between the regularization introduced by the diffusion and the oscillations introduced by the dispersion. And there is a kind of competition, especially near the discontinuity. This is what is important. Away from the discontinuities, when epsilon goes to 0, there is little effect of these terms. But near the shocks, these terms are very important, and they end up producing some sort of competition between various scales. And in the end, what you obtain are shocks that are not the classical shocks that were otherwise selected by only adding diffusion. And indeed, we get classical compressive shocks. I'm going to talk about that more in a few minutes. But more important, these non-classical undercompressive shocks, so that have different nature, different stability property. They are also called subsonic phase boundaries in the case of the example I told you about already. And so in the end of the day, you want conditions, algebraic conditions on the jumps that will allow you to select a unique solution for the Cauchy problem, or even before doing that, for the Riemann problem, where you only take a constant, piecewise constant initial data. So even this case is actually quite interesting. Okay, so I've been involved in this business for some years, and the key word that comes here is a kinetic relation. So this is what you need in addition to what is classically used, which is called an entropy inequality, so in addition to that, you need to prescribe a kinetic relation for undercompressive shocks. Okay? So essentially this is what I want to explain. What is an undercompressive shock and how do we select them by imposing an additional jump condition. Okay, so I've been doing some work about that, and first looking at the models. So I will spend some time to tell you that there are many models of fluids or solids when there is some complex behavior of these materials, where you actually see these phenomena that I'm talking about. Okay? So this is one part I'm going to discuss more. And then the second part I would like to tell you more about is how do we solve the Riemann problem, which is, as I said before, two constant states. There is a jump, and you want to know how this jump will evolve in time. Right? So this jump may be evolved just as a jump with some speed, or it could split into several waves, rarefaction waves, contact discontinuities, shock waves. Right? So this is what we have to understand, but to understand in a situation where we have these dispersive, diffusive terms in the picture, right? Okay, and then if this is something we understand, then we can, see where these kinetic relations will come from for a given regularization. So maybe I come back to that very quickly later on, but there are a number of theoretical issues that you can address if you know how to make this selection of compressive, undercompressive shocks. And then the next issue is to actually compute these shocks numerically, right? So there is something called schemes with control dissipation that play an important role. We have been able to compute kinetic functions. So maybe what I'm going to do today is show you the examples, try to explain how you solve the Riemann problem, and probably jump over to, depending on time, to show you some numerics and show you that these kinetic functions have actually been computed. They are really very concrete things that you can compute, and by computing these kinetic functions you can make comparisons between various models, between various schemes, etc., and see the effect of the parameters. Okay? And that are, of course, in the last part, I'm not going to cover that, but just to say that the story is not complete yet, so if you are interested in these problems, you are welcome to try to solve some of the open problems. And the open problems come when you have more than one inflection point in the flux, in this F. So I'm going to be more specific about this assumption in a minute. And also there are issues of non-uniqueness and connection with non-conservative products. So it's really a very active subject. Okay, so let me also say that I've been working with a number of collaborators and a number of students and former postdocs. And there are also many names I can mention here of people who worked on related issues of undercompressive shocks for various physical models, or looking also at multidimensional stability of interfaces, etc. Okay, so let's go on with the physical model. So before I show you really physical models, I'm starting with something very academic. And even before doing that, what I'm doing is reminding you of the classical case where to the scalar conservation law, you add only a diffusive term. Okay? So you can take even B to be equal to 1. It doesn't really matter. So here you have epsilon uxx, basically. So the way to analyze this equation is to take any function capital U to define so this will be called an entropy, the general function, but we call it an entropy in this context. Capital F will be defined by this formula and is called an entropy flux. And it's, of course, easy to make this calculation and observe that by multiplying your conservation law by the derivative of this entropy, you can obtain a divergence form for the left-hand side. And on the right-hand side, this was conservative. It was a derivative of some quantity. And you can also do that. So capital C is defined over here. So I guess there's some misprint because there is one X too much. But the point is that this part here is a derivative, some quantity. And what is left, it contains a coefficient b, the derivative of capital U, and a square quantity. Okay? So the conclusion that you draw from this simple calculation is that if U is chosen to be convex, then any limit, formal limit, but of course this can be justified rigorously, but any formal limit will satisfy this inequality in a weak sense, because think of U as U is discontinuous. U could be say an L infinity function or a BV function. And so on one side you end up with this measure, and this measure has to be negative because this goes to 0 in the limit, and this part has a sign. Okay? So this derivation is very, go back to the 60s maybe, and it just tells you that for every capital U you can derive an entropy inequality. So remember the question that we are asking, right? We have a singular regularization and we ask how can we characterize the limit of this singular regularization. Okay? So this is the answer in this very simple case. The answer is that you can write all of these inequalities for every convex U, and this is another way to express it, where instead of capital U of U, I'm choosing the so-called Khrushchev entropies. So K is a real parameter, but this somehow generates all entropies, so it's an equivalent statement. So either of these two statements, or there is another pointwise version due to Olenek. So there are various formulations of this entropy inequality, and any of these select a unique solution to the initial value problem. Okay. So that's somewhat the end of the story if you only add diffusion. Now what I'm doing here is I'm adding another term. Okay? So we have two parameters in principle. There is a beta and a gamma, and we try to do the same calculation, right? So I take, in principle, I might take any convex function, but what I'm going to claim in a minute here, there will be no sign for general convex entropies. So what I'm only doing here, I'm doing the same calculation as before, but only for U squared. Okay? And indeed, you see that one side can be put in a conservative form, and the other side has a negative term, which only comes from the diffusion, and a conservative term, which is due to part from the diffusion, and the rest comes from the dispersion over here. Okay? So the conclusion will be the same. If beta gamma goes to 0, at least formally, we're going to recover this entropy inequality, which corresponds only to the choice U squared. And so again, I repeat that if you would try to choose any convex entropy, it would not work, because there will be some extra term here that will have no sign, and in the same time they will not have a conservative form. Okay? So to have a conservative form, of course, is good if you look at that in the sense of distributions, and if you have a reasonable bound on the function U, you can indeed show that this converges to 0 in the sense of distribution. So what I said before is correct, that this is gone in a limit. Right? But if you have terms that are not of that form or that form, then you cannot conclude anything. Okay? So the conclusion in this case works only with the entropy U squared. Okay, now there is something else we can do. We can maybe compute numerically, this solution. So what I'm doing now is I'm taking beta and gamma very small, and I compute the solution of the initial value problem. Okay, to that. I will show a picture in a minute, but let me just say that the conclusion is that if you take these two parameters very small, but you take, oops, wrong button. Okay, but you take this parameter gamma, right? The second parameter, you take it converging to 0 much faster than beta squared. Then this case is a case where the diffusion dominates. And in the end, in fact, you don't see the effect of that term. So it's like you would not have introduced this term, and you end up having the entropy solution selected by the same Khrushchev inequalities or Olenek inequalities I just told you about. Now, there is a second case where you do the opposite. You take both going to 0, but beta square is going much faster to 0. And this is a situation where you will see a lot of oscillations that are due to this term, and no convergence. There will be a lot of oscillations, and more you refine your scheme, more oscillations you will see, and there will be no convergence at all, even no weak convergence. So what I really want to look at is a case where you keep these two effects in balance. And the way to do that is to take gamma and beta squared of the same order, where this kappa bar, this proportionality constant is indeed a constant, and gamma beta go into 0. So this balance regime, in this balance regime, what you observe is still strong convergence of this approximation to shock wave solutions. There are still mild oscillations, but they are not too bad. And what is most important is that in a limit, what we have is a competition between these two effects. And so the shocks that we select are not the shocks that we would have selected otherwise with this mechanism. And more than that, the solutions depend on this ratio of the two parameters. So this is kind of strange. If you are not used to that, you have a situation where in a limit you will completely forget about this part. Okay, that's what the game. We want to let beta gamma go to 0 and look at a solution of that part of the system. Okay, but when we do that numerically, for instance, we see that there is a limit, but the limit depends on some kind of a hidden scale that measures the balance between two effects, two competitive effects in your regularization. Okay, and so this is what we see. You have to so observe that there are two shocks in this picture. This is a scalar equation. So I guess most of you have seen equation maybe with a square here. So I'm looking not at so-called Burger's equation, but at an equation with a cubic flux. So you take that, and if you do what I said for balance, in the balance case, you see two shocks. If you go from, say, a bigger value to whatever. I mean, it depends on the end states, right? So I'm really solving a so-called Riemann problem. So initially, you had initial data that consists just of a constant state, then a jump, and then this constant state. Okay? And we look at the evolution of this big jump. And this jump, as time evolves, split into two waves. In this case, it is two shocks. If I change the initial value, so 4 has not changed, but here I've changed the bottom value here, then instead of two shocks, I get one shock, a constant state, one rarefaction. Okay? And if you know the construction in a classical case where the Oleinic entropy inequalities are imposed, you would know that this situation is not possible. So the only thing you can do with a non-convex flux, like a cubic, the only thing you could do is to get a rarefaction attached to a shock, or rather a contact discontinuity. So this is impossible with the Oleinic criterion. And also this is impossible. You could not have two shocks that are detached. Okay? But indeed, this is what we found numerically if we add dispersive and diffusive terms. And let me finish with this picture by saying that these oscillations, so there are mild oscillations near the discontinuities, but these oscillations disappear, they are gone when you take the discretization parameter to go to 0, right? So somehow this distance here is of order 20 delta x or something, you know, it's related to the discretization parameter. Okay, so there is really a limit which is made of a constant state, a jump, a constant state, another jump, a constant state, right? So this is what the theory should be able to tell us, that for conservation law we should be able to define that. Okay. So I give you more examples. Maybe I can go a little bit faster with these examples. So the so-called thin liquid film model consists again of a scalar conservation law, but instead of u squared, instead of u cubed, the flux is u squared minus u cubed. More importantly, the regularization is of much higher order. There are 4 derivatives. It's non-linear. It also depends on u. And this is really the first physical model you can think of. It has been studied by Bertozzi, Shearer, and some other people. And it contains the effect of surface tension on a film of liquid, I mean a liquid that move on a plane. And so it is described by this equation. So that's a very important model for some physical applications that has to be understood. Okay, so this is the observation I want to make. So connected with the previous calculations, this is the calculation I can make. So let's look at u log u minus u. So you can check this is a convex function. So if you take that to play the role of an entropy, like I had u squared before, you take it here, you define the flux in a similar way I had done before, so you get a conservative form. So you multiply, in other words, what I'm doing is that I multiply that by the derivative in u of this quantity. So I can make this left-hand side conservative. And then I look at the right-hand side, and the right-hand side works also well because I can put most of the terms in a conservative form, except one term, which is a square of some quantity with two derivatives. Right? So some of the structure is the same as before. It's different nonlinearity, different regularization, but different entropy, right? But still the same structure, that there is an entropy associated with this specific regularization. The entropy is convex, and we have a sign. And it works only for this entropy. Other choices would not give you a sign. I give you another picture for this model. You will see it's always, in this scalar case, the same kind of structure. You have two shocks or a rarefactional shock. So the order of these waves are different because we have a concave instead of convex flux now. Okay, and I continue with a generalized Kamasa-Holm model where we have two derivatives, three derivatives, but now we have a mixing of time and space derivatives. It's nonlinear, nu, ux, uxx. So again, this is a physical model that comes to describe shallow water dynamics, and it has been studied by a number of people. It has been, of course, introduced by Kamasa and Holm. And again, there is a single entropy inequality which is satisfied. It's a little bit more complicated, but the entropy is still u squared, and there is some additional term here. But otherwise, the structure is the same, and you get, again, a sign. Okay, and I want to emphasize properties that maybe I mentioned before, that what we get here, so we have changed the regularization, but it turns out that the solution looks similar but different from the other regularization I had before, where I put only u triple x, okay, not that. So what I want to conclude over here is that there is a dependence in the regularization. So changing the regularization, not just a parameter or something, but taking a nonlinear, another nonlinear regularization, possibly nonlinear, give you different solutions, different dynamics. Okay, so van der Waals fluids is a variant of what I had written before. So this is a part, essentially, the elasticity system I discussed before. But here we have nonlinear diffusion and nonlinear capillarity. Okay, and the story is the same. There is an entropy inequality. It's written here, a sign for the dissipation, and a conservative part. So now what plays the role of the entropy, it's a system now, not a scalar equation. So we have a part which is u squared like before, but there is another part which is a nonlinear function of this variable v. So I remind you that v is a volume, u is a velocity, p of v is some pressure function. It could, for instance, be given by this law of van der Waals gases. And based on that, you can define an energy by, roughly speaking, you integrate p, you get this epsilon of v, and that's the quantities that you want to conserve. Okay? And again, there are also entropies for that system, but the other entropies would not give you a good sign here. So this is the only one that can be used. Okay, so I guess this other picture will tell you, illustrate one point. The point is the fact that when you change the ratio of viscosity over capillarity, or rather viscosity squared over capillarity, I call it lambda. So if you change this ratio, this has some effect on the limiting solution. So what these pictures are showing you, they are similar to the picture for the scalar case, but they are for the system of two equations. So instead of one wave pattern, you see two wave patterns that correspond to two wave families. One going to the left, one going to the right. So if I, for instance, I look here, you have something like a shock or a phase boundary, and then you have another shock, right? So you have this two-wave pattern going to the right direction, and something similar to the left direction. And there is also the possibility to have a discontinuity, a constant state, and a rarefaction. Okay? So it looks maybe a little bit messy, but what I wanted to show in this picture is the fact that if you change this ratio, viscosity over capillarity, you actually change the limiting solution. Right? So again, I insist on the fact that this is not supposed to represent an approximate solution of some sort. Right? This represents every curve is supposed to represent the exact solution of a Riemann problem where all these regularization parameters or discretization parameters are gone. But even by doing that, I have several solutions for the same Riemann problem, and these Riemann solutions are parameterized in this picture by this ratio of viscosity squared over capillarity. Okay? So that's exactly, I mean, what I want to explain here is how there is we define a Riemann solver to handle these kind of things. And of course, you should realize immediately that we are not going to have a condition that do not in some way refer to this lambda, right? So there is some kind of hidden parameter in your regularization, and you want to keep track of that in the theory. So the theory should tell you that if you have a hyperbolic system, or it could be hyperbolic elliptic if there is phase transitions, if you have this hyperbolic system, you will not create a theory just by looking at the hyperbolic system. You have to introduce some ingredient, additional ingredient, which we will call this kinetic relation. Okay, so there is more. MHD, this is a magnetohydrodynamics, so it looks like a cubic flux. If you take W to be 0, first equation is a scalar cubic equation. And the same, the second equation, if you take V to be 0, would be the cubic scalar equation. But now there is indeed a coupling, V, W, like that. And on the other side, there are two parts. One part which is a regular diffusion. Nothing fancy for that. But more interesting is this part. It's still second order, but for some reason it introduces oscillations in your approximation. So there is plus alpha epsilon WXX minus alpha epsilon VXX. This is related to the so-called Hall effect in MHD. It's important to describe the solar wind. And V and W correspond to the transverse components of the magnetic field. It's essentially one-dimensional, and you look at the transverse components of this magnetic field. Epsilon is a magnetic resistivity, and alpha this whole parameter. So that's the model we have here. Again, there is an entropy inequality only for V squared plus W squared over 2. Only this one can be chosen. You have the negative term and the conservative term. And so that's another model you can play with for these things. So this is a result. Again, you see the structure: one shock, another shock, or with other numerical values, you get a rarefaction shock and a rarefaction. So all these pictures appear, and of course it's more messy, right? So I'm not so happy with the pictures, but in fact. This case is more tricky because of this regularization. I mean, somehow it's at the second order level, so numerically it's more tricky to somehow get nice pictures. But anyway, the phenomena is clear, where we do see again this two-wave structure. But observe that the examples I show you contains many different regularizations, right? And what I'm going to show you now is that all of these regularizations can actually be somehow summarized, or the information you need from this regularization can be summarized in a kinetic function. So I put even more examples here, which I've not looked at too much, but it seems that it seems that Buckler-Leverett equation, quantum hydrodynamics, phase field models, Sulicium models, some non-local models, or discrete models. So these models also exhibit undercompressive shocks, and this kind of two-wave structure instead of one-wave structure appear also. Okay, so for all these models, what you may have noticed is that they are rather complex wave patterns. We obtain different solutions if we change all parameters, everything we have at our disposal. And also you should observe that all the examples had a non-convex flux function. Okay, it was often like a U cubed or something similar. And in addition, there was always a single entropy inequality satisfied. Okay, now in fact, there is the case where the models are convex, have a convex flux, at least the scalar equations have this properties that one entropy inequality is sufficient to characterize a unique solution to the initial value problem. Okay, so if the flux is convex and you have only one entropy, which is what we have here, this is what I emphasize, then there will be only one solution characterized by that. So nothing to say from my point of view, right? And therefore, in this case, the shocks will completely be independent of any sort of regularization. Any scheme, anything you want to play with, all these small scales, they will have no effect on the shock wave solution. And so this is the reason that there is a nice theory, classical entropy solutions containing compressive shocks that are characterized also by lax inequalities. Okay, but what I'm working on is not convex fluxes, but are always non-convex fluxes. So what we need is somehow include macro scale effects, not resolve the small scales, and include these non-classical shocks. Nothing universal should be expected, but rather we should say that there are several hyperbolic theories that we need, and it's going to depend on the regularization. Okay, so let me move on with basically the second part. I mean, the second important part I want to discuss. How do we solve the Riemann problem? Okay, and I'm going to do that in a simpler situation of a scalar equation. So U will be just a scalar, and F is like U cube, right? I just take it slightly, say it could be U cube minus U if you like, but any shape with one inflection point will work. So that's what I'm assuming here. I need maybe some condition at infinity. And I want to tell you the construction of the Riemann solver in this case. Okay? And basically, if I tell you that, you will see the connections that have a way to understand all these examples in one setup. Of course, I'm only going to show you that for a scalar equation, but you have to believe me that for systems of two equations, as long as the system remains hyperbolic, it's similar. It's even very, very close to what I will tell you. And more than that, if you have a system of n equations, what I'm telling you for the scalar case can be basically repeated for every wave family. Okay, it's more involved, but essentially the same story that you repeat for every wave family, even though you work now with, you would have to work with vector-valued functions. Okay, so I need a definition from a U here, any point U on this graph. I'm going to use this point. So phi natural of U is a tangent point. So there's a tangent point here. Okay, and in a minute I will tell you that for every U, I will pick up a point which will be given by this kinetic function, and I will denote it phi flat of U, right? Of this U, UL here. And so every time I pick up a point using this kinetic function, I have a companion point which is simply the third point of intersection with the graph. Okay? And the last point, phi capital N, N stands for nucleation, and I will not talk about that today, so you can just take these 2 points to coincide. Okay, so what you see in this picture is that if I think of UL to be the left-hand side, and I want to solve a Riemann problem with some right-hand side, the right-hand side will be in this axis. So there is an axis here, and this is the axis for right-hand side. So what I need to tell you is if the right state is greater than UL, what solution of the Riemann problem do I get, right? If the right state is in another interval, what is the solution? In another interval, right? So there will be 4 possible patterns for the Riemann solution between this UL on the left side and UR in the axis, the horizontal axis. Okay, so that's what I want to get. So to do that, I first impose that U should be, the solution should be a weak solution. So a weak solution, I remind you that if U is in L infinity, you cannot write a PDE in a strong sense. But what you do is you multiply by a test function and you integrate by parts, right? So this is a way to define weak solutions. Now, the case where U has more regularity is of bounded variation, meaning that U sub t, U sub x are locally bounded measures. Then you can actually write the equation, but you have to think of ut as a measure and f of ux as a measure, right? And this is an equality between measures rather than functions. Okay, the shock wave solution. So this is an elementary piece that we need to solve the Riemann problem. We need shocks, we need rarefactions. So the shocks are simply functions that connect 2 constant states, u minus u plus, at some speed, lambda, right? So how do we get lambda? We write the jump condition. And the jump condition is something you can deduce easily from the conservation law, based on the definition I just gave you. And this is a relation. Minus lambda, the jump of u, the jump of f should be 0. And that gives you the speed of propagation uniquely. If u minus is distinct from u plus, this is how you compute the speed of propagation, right? 2 shocks, two constant states. You can propagate this discontinuity, and you propagate it with that speed. This is a weak solution for any u minus, any u plus. And then I'm going to call this ratio here, just a slope on the graph of f, I call it a bar of u minus u plus. Okay, so we are going to use these pieces to solve the Riemann problem. But we are not going to use all of them, because we need to impose entropy inequality. So some of these discontinuities will not be accepted, will not be admissible. The first requirement you could impose would be these so-called Oleinic entropy inequalities. So that would be to impose a condition like that. So let maybe not enter into the details, but there is some kind of a convexity condition that is imposed between u minus and u plus in order for the jump to be admissible according to the Oleinic entropy inequality, which is not the one I want to use. I just remind you that this is a classical entropy inequality, which is equivalent to the Khrushchev entropy inequalities I wrote before, also equivalent to impose all entropy inequalities. Okay? So this is not what I'm doing, but for the sake of comparison, it's good you have this in mind. So what I'm doing is imposing a single entropy inequality. Okay? So I want this to be negative across the discontinuity, where u is a fixed convex function, like u squared for the first equation, or u log u minus u for another model, etc. So this capital U is fixed once for all. And I compute the entropy dissipation corresponding to this quantity here. So that means I look at minus the speed propagation, the jump of the entropy, the jump of the entropy flux. And the only requirement I'm making is that this dissipation should be negative in order to satisfy this inequality. Right? So that's my condition for a good shock. Now, this is, you can rewrite this quantity here easily in this integral form, which is interesting because here you should recognize the quantity I just recalled to state the Oleinic entropy inequality. Okay? And in front of that, you see the second derivative of the entropy. So it should be obvious by just looking at this quantity that there is an equivalence between imposing all of the entropy inequalities and imposing the Oleinic entropy inequalities. Okay? Simply because this can be taken to be arbitrarily positive. Anything positive can be used here, right? So somewhere you can drop that and you get that this is a sign, and this should have a sign. Okay, but what I'm doing again is not varying capital U, but I fix capital U, right? So I'm looking at something like, this is like the Oleinic quantity but I only make some average of this quantity with respect to some entropy, fixed entropy. And this is what I conclude. I conclude that this entropy dissipation indeed has a correct sign, I mean, or has some classical shape, say, locally, but this entropy dissipation, how to say, so maybe you remember that I had introduced a tangent point before. Okay, so this part is normally the part which is selected by the entropy inequality. So given a U minus, I want to know what are all the points U plus here, which I can reach by an admissible shock. And the answer, if you use the entropy inequality, is that only that interval is allowed. Okay, but now because I'm only using one entropy and I'm only imposing a sign for this entropy dissipation here, I can go further. So this is a shape of the entropy dissipation, and it turns out that at this point, the tangent point, the entropy dissipation only achieves a minimum, but it is strictly negative. So if you continue further down, you have a whole interval where this dissipation is still negative, and you can introduce a point which I call the zero entropy dissipation function, this point here, where the entropy dissipation vanishes. Okay, so E of U, phi 0, flat of U is 0, and it's just another point where it vanishes, distinct from the original point. Okay, and a remark, maybe I'm not going to use that today, but there is a remark that says that from this point, if you draw the same picture, then actually you end up here. So if you iterate the zero dissipation function, you go back to U. So anyway, so the conclusion of this picture is that if you only impose one entropy, you are allowed to use this interval as an admissible interval for shocks. So that leads us now to the Riemann problem. We look at the list of all shocks, all waves we are allowed to use. So we are allowed to use all shocks that connect any point U minus, and let me say that U minus is positive, but of course there is also a class for U minus negative. But say U minus positive can be connected to any U plus between U minus and this tangent point. Okay, that's what I just discussed before. This is somehow the increasing part of the entropy dissipation. And all these points satisfy the lax shock inequalities. So if you look at the graph of F, you see this picture. I guess it's not so clear from here, but if you draw the trajectory of the shock and you look at the characteristic speeds on both sides. So I'm comparing F prime of U minus, F prime of U plus, and the speed of the shock. Okay? And you have some inequalities that relate these three quantities, and the inequalities are just telling you that the speed of the, say, of small perturbations on the left side, these small perturbations are absorbed, are compressed maybe inside the shock, right? And the same is true on the right-hand side. So everything somehow is absorbed, is compressed in the shock. Okay, now there is a second class of shocks that we allow with our construction, which are now will be called non-classical undercompressive, and they correspond to a discontinuity that connect a positive U minus, again just for definiteness, and a U plus, which is in the next interval where the entropy dissipation is decreasing. So it goes from the zero dissipation value to the tangent value, right? There is this interval here. And now if you look at the flux, the graph of F, you will see that the picture is completely different for the characteristics. What now you have is that on this side, it is faster than the speed of propagation. So the waves go through the shock, but then on the other side, they can exit because the characteristic speed is now faster. So this is why we call this shock undercompressive, right? So small, if you make a small perturbation here, a small wave, it will propagate, it will be deformed going through the shock, and then it will continue to propagate and forever. Okay? So this is a second class of shocks. We have both of them, and we have also the so-called rarefaction waves. Right? So you have seen before, we had shocks and rarefaction, so smooth solutions that actually only depend on this variable x over t, some scaling variable. So that's a classical part of the construction. I'm just looking at solutions that only depend on x over t, smooth solutions, plug that in the PDE, solve for u, and you get a formula that used to be f prime minus 1 over x over t. Of course, you have to be careful, look at the interval definition when this makes sense, and so on. So this goes back to Peter Lax in the 50s or 60s, and you end up find rarefaction waves that connect a constant state to another constant state by a smooth transition. Okay, and there is a whole class of such waves. And now, if you look at the characteristics by construction, you have that the characteristic speed on the left side is less than the characteristic speed on the right side, which is, of course, the opposite to what we had for compressive shocks. Okay? So things are spreading, and before you had a compression. Okay, so this is a third class of waves, and now, okay, maybe I can even possibly return to that later on, but let me conclude that now we can solve the Riemann problem by combining these waves together. And it turns out that we can get a solution, but in fact we can get many solutions. We get a one-parameter family of solutions satisfying a single entropy inequality. So this is a conclusion. If you have a non-convex flux with one inflection point, and you do this analysis, you look at all the waves that seems reasonable to use, then you have one but only one free parameter for every Riemann problem. Okay? So I think this is exactly the point where you understand that a kinetic function should be required, right? Should be maybe necessary and sufficient. So there is something else to impose, and that's what I'm doing now. And I told you a little bit that before. So now what I impose is that I'm going not to take any non-classical shock in a construction, but I'm going to take a very specific one. So for every UL, I assume that somebody gives me a kinetic function. So he gives me a map, phi flat of U. This point is picked up, of course, in the interval where I'm allowed to do that. So in this branch here, right, between the zero dissipation function, the tangent point, I pick up, the zero dissipation function should be further down. So I pick up this kinetic point in this interval, and this is a prescription. I'm given this function. And if this function is given to me, then I impose that the non-classical shock in a Riemann solver should only be the ones that connect UL to its image phi flat of UL. Okay? No other shocks, non-classical shocks is allowed. Okay? And if this is a rule that you impose, then everything follows, and you end up with this description that if the right state was bigger, you have to use rarefaction from UL to point further up. If you have a point in this interval, remember that these two states coincide now. So in this interval here, you use just a classical shock. You go from here to a point using a classical shock. But now if you want to cover the next two intervals, what you do is that you jump from UL to its image over here, and then you jump up using a classical shock to any point in this part. Or, and this is a two-shock structure that we have seen numerically, okay, non-classical shock plus a classical shock, or the other possibility to use a non-classical shock and to follow this part corresponding to use a rarefaction. And you get non-classical shock and rarefaction. And you should also observe here that you see the fact that the rarefaction is not attached to the shock because there is some angle here in this construction. Right? So normally the tangent are continuous. I mean, in the classical construction, the tangent will change continuously. But here there is some angle between the speed of the shock, which is the slope, and the speed of the rarefaction, which is given by the tangent to this part of the graph. Okay, so that's essentially the end of the construction of the Riemann solver. So you see that provided I'm given this ingredient of a kinetic function, I get a unique solution. Here I just give you some examples of curves, but of course I need some explanation to, I would need some explanation to tell you where they come from, but let me skip that. And maybe summarize by saying that, so we have this Riemann solver, right? For any two states, I know if I have a rarefaction, a classical shock, or two-shock structure, or a shock, a rarefaction structure. And these are two of the last two plots. and observe that there are no oscillations, what I'm showing you here, because this is really only constants and smooth regions. This is the exact solution of the hyperbolic equation. Okay? And before I was showing you numerical results somehow. So this is the exact theoretical results where no oscillations are left out. And let me conclude this part by saying that for systems of two equations, the same has been done. Essentially, the result is the same if the model is hyperbolic, but it's more tricky. And again, the work started with Marshall-Slemrod in this model. If you have a model which are decreasing parts, so the model will be elliptic if the stress-strain equation is non-monotone. There's an elliptic part. And as I said before, there is also generalization to systems of n equations. Okay. Do I have a few more minutes? 5 more minutes? Or it seems it's 25 over there, but.
Yeah, you may have 5.
Okay. Okay. So during the last 5 minutes, what I will just show you are numerical results. So I have to jump over a number of pages. So traveling waves, I skip that. Then existence of the initial value problem. Okay, I also am going to skip that. Zero diffusion dispersion limits, or using compensated compactness or measure valued solutions or kinetic formulations, you can actually justify for some models, mostly the scalar equations, possibly multi-D, you can justify some of this analysis. So I also skip that. Then we have been developing numerical methods to compute these non-classical shocks. So how do you get a scheme that indeed converge to what you want, right? What you have analyzed theoretically. So this is rather tricky. So I skip that, and I will just show you in the last 4 minutes some numerical results where we have indeed plot these kinetic functions, right? So you will see that I'm not creating that from my mind, but these things do exist and correspond to specific models. We have specific kinetic relations, okay? So, so here what we have is a cubic conservation law, right? Where now alpha is a parameter that describes the ratio of the two effects, right? So this is what we see here. If alpha is small, what I plot here are the results that correspond to various schemes, right? So I'm talking about a class of schemes. So of course I didn't tell you how these schemes are defined, but hopefully there is an order here, and as you increase the order, you should approach the exact solution, right? So that's basically what I want to show with these curves. It's rather boring here because it looks a straight line, but you can see in this other plot where, so this is a plot where you put u and phi of u, basically, right? So it looks like linear, but here it does not, and it's another plot where we are deriving the entropy dissipation as a function of the shock speed. And somehow physically it makes more sense that this quantity is called the driving force, and the driving force acting on the interface, and you want to know what is the speed of propagation of this interface depending on the force that acts on it, right? So it has some meaning, and you see some other curves and also some convergence effects, which is here. Okay, so I'm not, I guess I don't have so much time to enter into the details, and this is other pictures where what I've done here is making the diffusion larger, or yeah, I guess I'm confused because it seems to be further down. Okay, so it could be that this is larger dispersion rather than diffusion. So anyway, you see the effect of changing this parameter, you know, can be plotted. So of course, if you, for instance, if you only look at the Riemann solutions, you know, and you draw many Riemann solutions, for example, you will not see anything, right? Or it will be very hard to draw any conclusion. So the point of this kinetic function is that it stores all the information you need to know, and only that. All the dynamics of shocks is described by this kinetic function. So if you know that, you know what is the effect. If you know this curve, one of these curves, you know what is the effect of this regularization on the shocks, and you can then forget about the regularization. Okay, so time goes fast. So Kamasa-Holm, so I explained what it was before. So, okay, more curves. So this is a case where you have moderate strength, and I compare, so I made a comparison between linear diffusion dispersion and the nonlinear Kamasa-Hall model. Right? So I wanted to know what is the effect of these two. And it turns out that if the strength is not very large, they basically coincide. So we don't see, in the picture, we don't see the difference. But then we see the difference if we go for larger strengths. So you can see that the numbers are quite high here. And then there is some effect of the nonlinearity in the regularization that indeed is changing the kinetic functions dramatically. Okay? So you see that they are quite different. And okay, so that's what we see. And again, this is a van der Waals gas. If you look at the Riemann solutions, it's very messy and you cannot say too much what is going on here. But if you draw the kinetic functions, you describe exactly what's going on. You can change the capillarity coefficient. And if you change, you get different curves. You can change the order of discretization. You get different kinetic curves, etc., etc. Right? And I have maybe a last picture, which was more challenging, but very recently, actually, only last week, we made some progress on the magnetohydrodynamics and drawing also this kinetic function with the Hall effect. And I show you that it was more tricky numerically because there were more oscillations, but still we could draw that. And again, we have a picture in a phi of U plane. It is not so, okay, it's maybe so clear, but it's nicer when you draw it doing this numerical work. And especially for the thin liquid films, you know, in these cases, the regularization is so highly nonlinear that you can hardly hope for rigorous analysis of traveling waves. Right? But numerically, you can compute these things and observe a number of properties and make comparisons between various models and various schemes, etc. I guess I should stop here. Thank you.